Okay, welcome back to the next part of the lecture. Now, if you have noticed that in the nonlinear models that we discussed so far, we actually only discussed pooled estimators. So all the time we had this form that we have, for the likelihood, the product over n, the product over t, and we assumed everything is nice and there was no individual effects. There was actually, it was treated as if it was simply a big cross-sectional model. Now, what we want to do in the next part of the lecture, which is also going to be the final part of this whole course in terms of lectures, is we talk about how to include unobserved individual heterogeneity in nonlinear panel data models. Right, so we know that in linear panel data models, this is pretty straightforward. We do first differencing, we do the fixed effects approach, the alphas drop out, and everything is fine. Now, however, what we will see is that in the nonlinear panel data models, everything is a little bit more complicated. Yeah, so as I said, we have only considered pooled static models so far. And now what we want to do is that we kind of want to include individual heterogeneity, and we want to do dynamic models as well. Yeah, and while we talk about any nonlinear model, because we are in a likelihood setting, yeah, our running examples are going to be the binary choice models, so for instance, Logit and Probit. Yeah, so normally what we would like to have in the static case is a latent variable model where we include some alpha I0. Yeah, so in the alpha I0 is really our fixed effect. It captures all the unobserved individual characteristics that may be relevant, that may be correlated with X. So if we do not include the alpha here, it would normally be subsumed in the model error. And this would create endogeneity because this thing would be correlated with the X. Okay, now we include this alpha and we will see that this actually creates some issues, but we will see. As usual, we do not observe YIT star directly because, well, otherwise this would be a simple linear model. We would do first differencing and so forth, and then simply run a regression on the first difference data and get consistent estimates. However, we only observe YIT, which is kind of 1 when the latent variable is bigger than 0 and 0 otherwise. Okay, so for instance, like YIT star could be the expected profits from innovation. And then what we observe is only whether a firm innovated or conducted innovation in a period T. Now, if you have a dynamic model, then they usually look like this, where now this is important. YIT star is on the left-hand side. However, we normally assume that the dynamics are actually on the observed Y. So you see that there's no YIT star here. Yeah, so this, again, we only observe like this indicator function here. Yeah, we only observe YIT, which is either 0 or 1. And the dynamics are on the observed Y. Now, what we will do, as we did before in the last lecture, is that we will make assumptions on the model error, namely, meaning we fully specify the distribution of UIT in order to account for the nonlinearity of this model. Yeah, so we see that this is captured in the indicator. It's clearly a nonlinear model that jumps. So we have to take that into account by specifying the distribution of UIT. Now, if you look at this equation 5, then it's pretty clear why we need new strategies. Yeah? So for instance, in the linear case, we would simply take first differences on both sides. Yeah? So then we would have here delta YIT, which is the YIT minus 1. And on the right-hand side, the same thing. And the alpha would simply drop out of the model. Now, of course, this doesn't work because all the variables are inside this indicator function. Yeah, so differencing will not remove the alpha. Like another crucial difference is also that, well, if you look at the linear model, let's for instance look at this model, the alpha has the same effect on the YIT in every time period. Yeah, so in every time period you add the same fixed effect. Now, in the nonlinear model, you also add the same fixed effect, but through this indicator function, the effect of alpha itself on yit depends also on the other variables, on xit and on yit minus 1, right? So whether, alpha may push all the variables over 0 in period 1, but it may not do so in period 2. Yeah? So the effect of alpha itself actually varies with the levels of the other variables that we have in our model. So that's another crucial difference that arises because we have a nonlinear model. Okay, now what do we do? This is a crude overview about what we will discuss. There's like two schools on how to deal with this. And the first thing is the random effects approach. Now, we learned about the random effects approach already in linear models, where we simply assumed that, well, the alpha is uncorrelated with the axis, so we can put it back into the error term. And well, the random effects estimator then simply exploited some more structure in the variance matrix that is induced by, well, the random effects assumption. Now, in nonlinear models, it will not be enough to only assume that the alpha is uncorrelated with the u. Yeah? Because, well, if you were to put the alpha in the u, and you need to specify the distribution of the unobserved model error in order to deal with the nonlinearity, well, just knowing that alpha is uncorrelated with u will not be enough. If you want to call this thing here the new model error, then you actually need the distribution of the new model error. Yeah, so, and if you only know the expectation of alpha and u, of alpha actually, right? The correlation between the two things, this will not be enough. You need the full distribution of this term here, of the full unobserved part. And therefore, we need to make even stronger assumptions in the nonlinear case when we want to apply random effects. Now, on the other hand, we can use fixed effects. So in the fixed effects approach, we leave the distribution of alpha I0 completely alone. We don't make any assumptions on the distribution of alpha. Now, this sounds, of course, much better, a much, much weaker assumption. However, there's also a big downside of the fixed effects approach, namely, the fixed effects suffers from the so-called incidental parameters problem. And this is an incredibly influential paper by Jerzy Neyman and his PhD student Elizabeth Scott. And in particular, Jerzy Neyman, I'm pretty sure you heard the name before, is one of the greatest statisticians ever, and particularly of the 20th century. Now, before we discuss the incidental parameters problem in the famous Neyman-Scott model, let's introduce a little bit of notation. Well, this YIT is simply the whole time series of the outcomes, and XIT is the time series of the explanatory variables. And what we assume is that we know the density. Yeah? So we know the density of Y conditional on the axis and the alpha. And what we want to find out is this parameter theta here. Yeah. Okay. Then we take the log of this thing and we scale everything by a factor 1/t. This gives us the scaled log likelihood. Okay, this is only notation. What we assume in the following is that we have IID across IID sampling, and the likelihood is, as usual, well behaved, meaning we can take as many derivatives as we like. These derivatives will be continuous. We can interchange taking expectations and taking derivatives, all these kind of things. Okay, now, if we were to estimate these models with fixed effects, what would we have to do? Well, first of all, we notice that the alpha is unobserved. We cannot deal with models where something is unobserved, some of the data is unobserved. Yeah. Again, in linear models, we would kind of do first differencing, the alpha drops out, and then there's actually no need to deal with this unobserved factor anymore, right? In nonlinear models, we have to do something about it. So what we have to do is that actually we have to estimate alpha together with the parameter of interest theta. So we have to estimate what effect alpha has. Now, because of this estimation step, we can actually regard alpha as an additional parameter, right? So this is like a little bit confusing maybe. Alpha in our interpretation is always a random variable. It captures all the individual specific characteristics that may be relevant and that do not vary over time and that are unobservable. Statistically, however, because we have to estimate this alpha, it can be regarded as if it was a parameter to be estimated. Now, the problem in the fixed effects approach is that the estimation of alpha cannot be separated from the estimation of theta. So our estimator of alpha will depend on theta. Right, so for instance, our estimator of a normal of the variance of a normal distribution will depend on the estimates of the mean, typically, right? Now, what would we do? We apply the measured maximum likelihood idea. We simply maximize the alpha component for any value of theta. And so this gives us this alpha hat here. Yeah, for any value of theta, we maximize the likelihood in the alpha component, yeah, with respect to u here. Okay, now when we take this alpha and we plug it into the likelihood, which simply means we estimated the effect of the unobserved alpha, and now we plug it back in the likelihood, yeah, so that we can estimate theta. This object here is called the profile or concentrated likelihood. And this is like hugely important in statistics and econometrics. Now, you do this for every individual because each individual has a different alpha. So you have to do this for every individual. And then you simply average or sum across individuals, like you sum these profile likelihoods across I, and you maximize again with respect to theta. And this thing here, theta hat, is then the fixed effects maximum likelihood estimator. Okay, now let's think again back to our discussion of maximum likelihood. What we learned is that maximum likelihood is consistent and it is correctly centered asymptotically with the normal distribution. And it was also efficient and it was wonderful. Now, here, unfortunately, we are not in the vanilla maximum likelihood scenario. So here, the dimension of the parameter to be estimated is not fixed. It's not p, it's not k. No, it increases with n. Why that? Well, because each individual has an individual specific alpha I0, and each of those alpha I0s acts as if it was a parameter to be estimated, and therefore, for any individual that we get in our sample, we have another parameter. And as n goes to infinity, the dimension of the parameter that we estimate also goes to infinity. And this really causes problems. Yeah, so we cannot use the standard maximum likelihood theory. Now, Jerzy Neyman and Elizabeth Scott noticed this already in 1948, so a long time ago. And this model has sparked like a huge literature, both in econometrics and statistics, and this literature is still ongoing. And the model is extremely simple. Let's say we have a model, yit is equal to alpha I0 plus uit. Let's make it even simpler. All the u's conditional on the alpha are IID normally distributed with mean 0 and variance sigma naught square. So what we see is that the heterogeneity arises in the mean of yit. Yeah? So yit itself will be normally distributed with mean alpha I0 and variance sigma naught square. Okay, let's go back to our theta notation for the parameter of interest. So we want to estimate this thing here. Therefore, we can write the likelihood depending on theta and alpha simply as the product of the individual normal densities. Yeah, so this is the normal density, and we simply take the product across T because we assume independence or actually IID data across T. Okay, this gives us this expression here. Yeah, so nothing changes. This one turns into a T, and the exponential function simply gets this summation here. Now, of this expression here, we will now take the log and we will divide that expression by 1 over t, which gives us this expression here, the log likelihood. Okay, now let's calculate the profile likelihood. In order to do so, we need to find alpha hat. So alpha hat, remember, is the maximizer of this thing in the alpha component. So in order to maximize it, we take the derivative of this with respect to alpha and set it to 0. Yeah, so there's no alpha here, there's only an alpha here. And if you solve this for alpha, what you see is that no matter which theta you pick, alpha hat will be the time series average of y. Now, taking alpha hat and plugging it here gives us the profile likelihood. Yeah, you see where each of the alphas is simply replaced by yi bar. So this thing here is the profile likelihood. Okay, now, is this good? Well, let's see. Well, what do we know about proper likelihoods? Well, for instance, we know that the genuine likelihood is score unbiased, meaning that if I take the derivative of the likelihood and I evaluate it at the true parameter value, then the expectation of that thing will be 0. However, for the profile likelihood, in this simple model here, we see, you just do the algebra. So this thing here will be t minus 1 theta naught. This is actually just the expectation of the sample variance. You can check it. What we see is that the expectation of this thing is non-zero. Yeah? So this thing here is not 0. In fact, the bias is of order 1 over t. Okay, now you will ask, why is this even interesting? Well, because in the standard theory, we need score unbiasedness for consistency of the maximum likelihood estimator. Okay, so that's bad news. And indeed, if you look at the maximum likelihood estimator, which can be written as this thing here, and you take the expectation, what you will find is that the expectation of theta hat will coincide with the true value, but there is a bias term. And this bias term is of order 1 over t. So if you let n go to infinity while you keep t fixed, actually theta hat will be inconsistent due to this additional term here, this bias term. Okay, now the next thing to notice is that if you were allowing t to go to infinity as well, this term would vanish, and actually asymptotically the bias of theta hat would disappear. So we are back in a consistent case. That sounds good. However, good. Yeah, that's what I'm just saying. So for fixed t, it's inconsistent. If n and t goes to infinity, it's consistent again. However, what Neyman and Scott have also shown is that when you look at the asymptotic distribution, what you find is that if n and t grow at the same rate, we have first of all a bias in the asymptotic distribution. So this part here is not 0. Then if t grows faster, okay, so here the limits are taken as n and t go to infinity, of course. I will have to fix this, sorry. So in this case, where t grows faster than n, then actually we have a nice asymptotic distribution. Yeah? So this can be used for inference. However, if n grows faster than t, then this distribution doesn't even exist. It completely explodes. Okay, so we have a bias when n and t grow at the same rate. We have a nice distribution if t grows faster than n, and we have a terrible thing if n grows faster than t. Okay, now, what does this mean in practice? Well, let's discuss the general case. Like the insights from Neyman Scott actually carry over to a general nonlinear panel data model with fixed effects. You can show that the MLE minus the true value is a nice thing. Yeah? So this is the asymptotic normal distribution plus a first order bias. So if n goes to infinity, this term here disappears. However, this term here stays, and therefore the MLE is inconsistent if only n goes to infinity while t is fixed. If you let both n and t go to infinity, both these terms disappear. But if you look at the asymptotic distribution, this is again the correctly centered normal distribution. This is good. However, here we have a term that does not disappear unless t grows faster than n. So in order to make this vanish, we have to assume that t grows faster than n. And of course, this is absolutely insane to assume in microeconomic panel data sets, where we have, for instance, 10,000 firms observed over 5 years. Yeah. So what you see in simulations is the maximum likelihood estimator has a huge bias in short panel data sets. Yeah, so it's pretty useless. Okay. Now, let's take a look at a more interesting example. Like the Neyman Scott example is very insightful, but it's not really of practical relevance. Let's say we want to fit a static logit model with individual effects. Then the likelihood for the whole sample can be written like this. Yeah, so this is something that we've seen before. Now the only difference is that we include these alphas. What we've also learned already is that we cannot solve for anything actually. Yeah? So the model is too nonlinear. We cannot find any closed form expression for alpha hat. We cannot find any closed form expression for the maximum likelihood estimator. Okay. However, you can find a closed form if you make additional assumptions. Yeah? So if you simplify the model, it can be shown with quite a bit of algebra, which I want to skip at this point, that if you have only 2 time periods and you set the first x to 0 and the second x to 1, yeah, so you make this really strong assumption, then you can show that the profile likelihood is non-existent if both y's are 0. It's also plus infinity, doesn't really exist if both y's are 1. And the only thing that makes sense is when either y1 is 1 and y2 is 0, or the other way around. So what this thing here shows is that actually the parameter is not identified for individuals where the outcome does not vary over time. And this makes also perfect sense, right? So kind of when you have a time constant outcome, yeah, so for instance, yit is always 1, and this is unobserved and completely unrestricted. Well, if we choose this thing to be plus infinity, well, then this is naturally satisfied. Yeah, so if this is always 1, then like a very large fixed effect explains this perfectly. Yeah, so there is no information needed from X. Absolutely useless. Yeah? Like time constant outcome can be perfectly explained by the unobserved effect. Yeah? We cannot distinguish this model from this model, right? Where the alpha simply takes over absolutely everything. Yeah? Okay, good. So this was important for identification. We need variation across time for the response variable. Now, in this very simple example, where t is 2 and the x's are chosen like that, we can actually show that the MLE is inconsistent, and the inconsistency is pretty large. Yeah, so theta hat converges to twice the true value. Yeah, so this is pretty bad. Now, of course, this doesn't come as a surprise. We know that the MLE will be inconsistent. However, the good news in the logit example is that we can do some fancy trick. And this fancy trick will allow us to get a consistent estimator, even if t is fixed and only n goes to infinity. And the trick is that we will condition on a so-called sufficient statistic. Okay, what is that? Let's consider first the simple case, t equal to 2. However, let's not restrict the axis in any way. First of all, we have known already that if we include fixed effects, we can only use observations for which this condition holds. Yeah? So with variation across time in y. Now, if you look at the probability of yi1 conditional on this condition being satisfied, oh, sorry, there should be an equal to 1 here. Sorry. Then by the definition of conditional probabilities, it's simply this, right? The joint probability divided by the marginal probability of this thing here. And well, the joint probability of this thing, if I know that yi1 is 1 and I know that these things together are 1, I know for sure that yi2 has to be 0. And by independence across T, I can write that as the product of this times this. And similarly, this thing here, there's two ways in which I can make the sum equal to 1. The first is that yi1 is 1, yi2 is 0, and of course the other case. That's pretty clear. Now, we will kind of work with this form and we will show that, well, actually it does not depend on alpha I. So let's look at this. We know what this is. So by the definition of the logistic PDF, this is simply the definition. And if the y is 0, well, it's simply 1 minus lambda, which can be written as this. Okay, so by independence across time, this term here on the numerator will be this. Yeah, and also in the numerator, in the denominator, we will have these terms, right? So this term here is exactly this, and it can be written like that. Okay, so this is, of course, let's say, you know, if you cannot follow, of course, while I'm talking, it's because it's a terrible amount of algebra. But please take a minute to just look at this in a little bit more detail while you go through the slides. And the calculations are actually pretty simple. And so if you plug in all these terms, then you see that here the denominator 1 plus x1 times 1 plus x2 is the same also here. Yeah? So here we have a fraction divided by a fraction, which means that the fraction is multiplied by the inverse of the fraction. So this thing here in the denominator will actually cancel out. Okay, so far so good. And the next thing that we can do is that we take, so we're now in this expression here in the second equation, and now we can take this thing here common, or we can actually take the negative of it common. Or basically we multiply the numerator and the denominator by the exponential of minus xi2 theta minus alpha I. And what we get then is that in the numerator, there is no alpha. And in the denominator, there is no alpha either, right? So this one is simply this multiplied by this. Oh. Magic, right? So by conditioning on this statistic here, we have found an expression that depends on theta, but that does not depend on any unobserved alpha. Of course, we can use the same argument, you know, for yi2 equal to 1. And as I said, the important thing is that these expressions, they do not depend on unobserved variable. So this thing here is a sufficient statistic because, well, knowing the statistic is sufficient for knowing the unobserved alpha. Now, this was the case for t equal to 2. You can, of course, do the same, apply the same idea for t larger than 2. And the sufficient statistic is simply the sum of the y's. And it can be shown that this thing here, this conditional density, does not depend on alpha. And if you are interested, here, this is the reference in the Wooldridge book with slightly different notation, but the idea is exactly the same. Okay, this density conditional on the sufficient statistic is a conditional density, and a conditional density is still a density. And therefore, we have a density that we can use, define as a likelihood, a conditional likelihood in that case. And that conditional likelihood only depends on theta. And because we are back in the likelihood case that only depends on theta, the dimension of theta is fixed, does not increase with n, we can apply the standard maximum likelihood theory. The standard maximum likelihood theory applied to the conditional likelihood gives us the conditional maximum likelihood estimator. And this thing is again consistent no matter what value t has. So we completely circumvent the incidental parameters problem. And well, the same trick with conditioning works on more models, not only the logit. It works actually in all models from the exponential family. For instance, the Poisson model. However, of course, there's also a downside. This conditioning is very, very complicated and many times actually impossible once you have a dynamic model. So we looked at static models. Once you go to the dynamics, it's a mess. And moreover, even though conditioning works in the logit, it does not work in the probit, even in the static case. And this may be a little bit surprising because like the logistic density and the normal PDF, they look pretty similar. The logistic had just a little bit fatter tails. Yet this conditioning works in logit and it does not work at all in probit. So that's the downside. Okay, so if we cannot condition because we cannot find a sufficient statistic, what do we do? Well, one thing would be to apply bias corrections, which we will discuss at the end of the slides. So with bias corrections and fixed effects, we can reduce the order of the bias from 1 over t to 1 over t squared, so that the bias is kind of removed very quickly as t increases. And what simulation shows is that these bias corrected estimators, they improve like tremendously upon the MLE. So really it's incredible. They work much, much better. Yeah, we will discuss a little bit about how to derive these formulas, but the formulas are quite complicated and we will not discuss them in detail. Now, what you can also do when you cannot find a sufficient statistic is, and this has been traditionally done, like even before the bias corrected estimators have been derived, is that you use random effects models. Okay, so you circumvent the incidental parameters problem by actually modeling explicitly the distribution of the unobserved effect. So, and what you should do is not only, you should actually allow for correlation between the alpha and the observed axis. And thus, what people do is normally a so-called correlated random effects approach. Okay, now what is that? A very popular approach is due to the good old Wooldridge. This is a paper in the Journal of Applied Econometrics, highly cited. And Wooldridge discusses how to use random effects estimator or how to derive random effects estimator that can be estimated with standard software. So no need to do anything new. And in particular, he derives a dynamic correlated random effects probit model, which is hugely popular and that does not suffer from this initial. So first of all, it does not suffer from the incidental parameters problem, and it does also circumvent the initial conditions problem, which is again something new. So only problems. The initial condition problem arises because whatever we see in our panel data set, the first observation in time that we have is pretty much never the first observation of the process that we observe. And even if we observe the whole process from the start, then we need to allow for dependence between the initial y, the starting value of the process, and the unobserved effects. For instance, like let's say we observe a cohort of students after graduation and we look at their employment history. And the y is simply an employment indicator, yes or no. So would you think that yi0, the initial employment indicator, should be correlated with unobserved effects? Well, sure, right? There is unobserved individual characteristics that are kind of relevant for your success on the job market, and thus alpha is not independent from the initial condition, for sure. Okay, how to do this? Well, okay, where are we? Oh yeah. Okay, let's discuss state dependence first. What does that mean? So we have two things that we need to address in dynamic models. First, the initial condition problem. Actually, we have a multitude of things. We have the initial condition problem, we have the incidental parameters problem, and we have this state dependence. Okay. Yeah. If you look at dynamic binary choice models, you have what is called state dependence, meaning if you have like success in period t minus 1, you're more likely to have success in period t, and the other way around. If you have failure here, then the chances of failure are larger here. So what you want to do is that you want to have a dynamic model, and that still allows for unobserved individual effects, because what you want to have is a model that disentangles true from spurious state dependence. So what do these things mean? True state dependence means that there is actually a structural effect of experiencing success in previous periods. So if I experience something in the past, I am more likely to experience it in the future. So for instance, if you look at innovation, you only look at whether a firm innovates in a particular period or not. Then it is often regarded, like often seen that like when you innovate in period t minus 1, this has a structural effect on the chance of innovating in period t, because, well, if you have innovated in t minus 1, you have sunk costs, you have invested in labs and research material, and also you're more likely to keep going because you're learning by doing. You're actually getting better at research and innovation. Yeah, so there's a structural effect of experiencing innovation in past periods. Now, this is different from spurious state dependence. So spurious state dependence comes precisely from the unobserved effects. Now, each of the y's contains alpha in each time period. So there is naturally some dependence across time just because each y shares the same factor alpha. Okay. Now, okay, so even if like my experience of innovation in the past has no effect whatsoever on my chance of doing innovation in the current period, just because the alpha is there, it will look like there is some sort of state dependence. Yeah, so just the alpha will make it look like there is due state dependence, but there isn't. Thus, what we need to do is that we actually have to put like these individual effects in the model in order to account for them so that we can disentangle the true from the spurious state dependence. And so what would be, for instance, like an example of spurious state dependence? Well, let's say that firms are actually, very different in terms of their risk-seeking management. So some firms have very risk-seeking management. They go for innovation, whatever happens. Think of like Google, for instance. They innovate no matter what. So that's like a risk-seeking management. And this is driving their innovation, not whether they have been kind of doing innovation before. They don't care. They would innovate whatever. Now, if you do not control for these unobserved characteristics like a risk-seeking management, then it would look like Google is actually innovating because it has innovated in the past. So it would look like there is a structural effect of past innovation because past innovation is actually acting as a proxy for the alpha, for the unobserved characteristics. Yeah? Okay, quite a lot, I know. Anyway, let's move on. What does Wooldridge do? Wooldridge proposes to simply model the distribution of alpha depending on the observed covariates, the initial condition, because this allows for dependence between the alpha and the axis, and also between the alpha and the yi0. Okay. Now, we said already that he models the distribution, which means he really models the density of alpha conditional on x and the initial condition. Now, once you have that, doing maximum likelihood is actually really simple. Yeah, so for instance, we look at the conditional density here, which is from our original model. And now we integrate out the alpha with respect to its density. Yeah, and then we simply get the marginal density on the left-hand side. And here you see that there is no alpha anymore. Yeah, so we have integrated out alpha, and this thing here only depends on theta. So you do standard vanilla maximum likelihood and you're fine. Depending, of course, under the assumption that this thing here, the distribution of alpha, is correctly specified. Yeah, so that's exactly what I said. What Wooldridge, like, he does this in his famous dynamic probit model. Yeah, so this is what the model looks like with the original fixed effect, or not fixed effect, sorry, unobserved heterogeneity. Of course, there's underlying assumptions, for instance, that like the lag order is correctly specified, so there's only one lag here, not two. Then of course the x's have to be strictly exogenous, and the unobserved heterogeneity has to be additively in like this phi function. So it gets more complicated if it's multiplicative. Anyway, Wooldridge then says, okay, let's simply specify a linear function for alpha I0. So we have an intercept, we have something that measures the dependence on the initial condition, and we have something that measures the dependence on the axis. And in particular, he says, let's take the average of the axis because it makes the model more parsimonious, meaning like fewer parameters. Yeah. So here we have the dependence on the observed axis and the initial condition. And then we say this thing, whatever remains, this is just noise. This is just normally distributed with some variance sigma squared. Yeah, so this is independent of everything else. And then we know that the alpha has this distribution here. Yeah. And the mean of alpha is allowed to depend on x and y. And yeah, that's the big advantage here. So we have a correlated random effects model. Now, let's take this and plug it in here. So this is precisely what we get here. And well, the likelihood is pretty much the same as we have known before. Yeah. Now, depending on alpha, on the A actually. Yeah. So these alphas here are now parameters, non-random, and this is the only random part that is left in the model. Yeah. So the likelihood is given by this for each individual, where of course the dot 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 means that everything in here goes into the dot dot dot. So beta contains all the parameters. Yeah, so we have now a couple of additional parameters because we have this correlated random effects model. And yeah, for any given value of AI, the random effects model is now a standard probit model with some additional regressors. So really standard. And if because alpha is unobserved, what we need to do, as we discussed, is that we integrate out, sorry, the AI, it's now the A. It's not an alpha here. The A is unobserved, so let's integrate it out because we know that A has this distribution. So easy peasy, we can simply integrate it out. And once we do that, we get this likelihood on the left-hand side, which does not depend on alpha, A, or whatsoever. Yeah? So therefore, we can apply vanilla maximum likelihood theory, take the log and maximize, and this gives us the condition, the correlated random effects estimator. Okay, and if all of our assumptions that we made are actually true, then this thing will be consistent if n goes to infinity and t is fixed. Perfect. Now, of course, the big disadvantage of the correlated random effects approach is that we have to specify this distribution here, and we have to specify the exact form of the unobserved effect. And for instance, if this distribution is misspecified, then our estimator will be inconsistent. And if the dependence structure is more complicated than what is written here, again, the estimator will be inconsistent. So let's try to relax all those assumptions. Let's go with the MLE in fixed effects again. Yeah. In rather recent years, so these things are not yet that old, there have been bias corrections of the fixed effects estimators. Yeah, so this is so recent that I'm not sure if that's even discussed in the Wooldridge book. What we want to do is that we want to mitigate the incidental parameters problem without making any distributional assumptions on the unobserved effect. Now, how would we do this? As we said before, is that we reduce the order of the bias from 1 over t to 1 over t squared. Yeah, so we remove the first order bias. And if you then look at the asymptotic distribution of these bias-corrected fixed effect estimators, then you see that this is the nice normal part, and this is the new remainder term. So remember, for the MLE, this was n over t, so that we require t to go to infinity faster than n. However, here, we can allow n, for instance, to grow at rate t squared, and this thing will still go to infinity, to 0 if n and t go to infinity. So we can allow n to grow faster than t, and this is much nicer for our microeconomic panel data sets. Okay, so there is really a multitude of methods that remove the first order bias. So let's do a very simple one. First of all, what we do is that we expand. Sorry, there should be another expectation here. I will fix that. We expand alpha hat around alpha star, where alpha star is not the maximizer of the likelihood in alpha, but it's the maximizer of the expected likelihood. Yeah? And this makes a huge difference. Yeah, so we do a simple Taylor expansion, and this gives us this term BIT here, plus a remainder term that is of low enough order. This thing here is the so-called target likelihood. And if we had that target likelihood, it would solve all our problems, because it's like fixed t consistent, it's correctly centered asymptotically, it satisfies like the score unbiasedness, the information equality, it's perfect. We would like to have that. However, this value alpha star depends on the unknown parameters through this expectation here. Yeah, so that's bad. It's actually infeasible. We will never know alpha star. However, what we can try is that we can get closer to the target likelihood by removing the first order bias from the profile likelihood. So this is what we're doing here. So we define this L tilde, which is the profile likelihood, corrected with an estimator of the first order bias. And it can then be shown that the bias of this L tilde, this bias corrected likelihood, is actually of order 1 over t squared. So we have removed the first order bias. And if we maximize these likelihoods, then it can be shown that we get this nice error term here, with which we can allow n to grow faster than t. Now, this thing here is an explicit bias corrections. There's also a multitude of implicit bias correction, and here I'm advertising actually one of my papers. So this came out recently in the Journal of Econometrics, where we do a bias correction based on integrated likelihoods. And it's rather technical, but if you're interested in this particular topic, this is still an active field of research. And if you have any question, please go ahead and ask. Okay. Finally, we now discussed like the estimation of the coefficients, but as we have learned, many times we actually care about the average partial effects more than the coefficients. And as for the coefficients, whenever we have a fixed effect or an unobserved effect, we cannot estimate the APEs directly because, well, as you can see here, there's unobserved variables inside the APE. Now, what we would do with random effects is again, of course, we take our likelihood where we have integrated out all the alphas, and we calculate the APEs based on that likelihood. And for instance, for the Wooldridge paper, it looks like this. Yeah, so we plug in all the estimators for the parameters, and the A in the index simply means that we have to scale all the parameters with this thing. And this is, well, I'm not sure if this is very understandable, but this is necessary because by adding the AI, we changed the scale of the original model error. Yeah, so normally the model error in Probit is assumed to be normally distributed or standard normally distributed with variance 1. But once you add this AI term, the variance is not 1 anymore. Yeah, so the variance is actually 1 plus sigma squared in the square root. Yeah, so you have to take that into account. In fixed effects, again, you would apply the idea that everything that is unobserved, you estimate. Yeah, so instead of the alpha 0, you plug in the estimator alpha hat. And yeah, because you have this alpha hat in there, you have again an incidental parameters problem. However, we have learned already how to fix that. We do some expansions and we try to get this thing, alpha hat, closer to the target value. And if we plug in the target value here, everything is perfect again. So if we can get close to the target value, we are doing fine. And yeah, so there's also bias corrections for the APE. So let's summarize what we have, like fixed versus random effects. In nonlinear models with fixed effects, you typically have to deal with the incidental parameters problem. Whereas when you assume random effects, you are likely to have a misspecification bias. Now, let's say you care about the coefficients. Then it turns out that the fixed effects estimator and the random effects estimator have a bias of order 1 over t. This one because of the incidental parameters problem, and this one because of misspecification. So when you have a very long panel data model, panel data set, so let's say with 30 time periods, it actually doesn't matter so much whether you use fixed effects or random effects, because like you have enough signal in order to estimate the alphas with both approaches. Everything fine. However, if t is small, you should use these bias-corrected fixed effects estimator because, well, these have an error of order 1 over t squared instead of 1 over t. Nevertheless, to be fair for the random effects, if you are very sure of your distribution that you impose on the alpha, of course you should use random effects, because random effects is, after integrating out the alphas, efficient. It's perfect because we use the vanilla maximum likelihood theory. Yeah, so if you're very sure about your specification, random effects is the best. Otherwise, for small t, fixed effects is probably better. And this is particularly true if you look at the partial effects. Again, fixed effects has a bias of order 1 over t, which can, using these fancy methods, be reduced to 1 over t squared. However, if you do random effects and you have a misspecified model for the random effect, then actually the bias is of order 0.1, so it does not disappear as t goes to infinity. So what does it mean for you in practice? If you if you are not very sure about the model, about the density of your unobserved effect, and you're interested in estimating APEs, you should probably use bias-corrected fixed effects estimators. Okay, so as I said, the last stuff is still relatively recent, so still active research. If you have any questions regarding that, please feel free to ask. Okay, see you in the tutorial.